Good evening and welcome to the Exploratorium, to After Dark, and to this presentation of Everything Matters, Tales from the Periodic Table. Certainly our longest titled talk ever in the history of the museum. I'm Ron Hipschman, and I'm going to be your host tonight for Everything Matters. And tonight, our element is copper. So we have made it quite a bit of the way through the periodic table now. We're getting to get to some of the really interesting stuff. I hope that you all got your collectible card. You got your copper card. And you'll learn why both of those things are on the card tonight. If you are filling in and you haven't been to Everything Matters before, I believe that some or all of the previous 28 cards may be over on the tables at the entry to the Phyllis C. Wattis webcast studio. So collect them all. They're kind of like Pokemon. So how many people have been to After Dark before? Raise your hand. Oh, how many people is your first time? We'll do the compliment. Cool. Okay, so there's something that is really an amazing thing that we have here. We have an After Dark membership, which if you join as an After Dark member, it entitles you to come to 52 After Darks, which would be like $1 a piece, or less actually. So it's a really great deal. So if you enjoy yourself tonight, consider the After Dark membership. It's very cool. So tonight's program on copper, we're going to do about 60 minutes, half me, and I have another speaker here. I'm going to talk really sort of a little bit about the qualities of copper and its history and where it comes from and some of the uses of copper. And then we have a guest speaker, Ashley Adams, and she is doing research on spiders. And she's going to talk to us about how spiders are related to copper. And it may surprise you. So, let's begin. Copper is we're making our way down through the periodic table. Right there in the periodic table, it's element number 29. It's atomic number 29. And that just means that it has 29 protons in the nucleus. And it has a variable number of neutrons, and we'll get to that later. But if it has 29 protons, it's copper. It tastes like copper, it acts like copper, it quacks like copper. So that's what says it's copper, is the number of protons in the nucleus, because that means there's also 29 electrons surrounding that nucleus. Now, copper was one of the very few metals that is actually occurs in nature natively, and it occurred on the island of Cyprus, so it was given this name, which really kind of means metal of Cyprus, but that kind of got changed around, became cuprum, which is the Latin, I believe, and then that got changed to copper. So it's been known for a long, long time. Excuse me, I got a cough here. There we go. It's mined in lots of different places in the world, and there are some beautiful, beautiful, beautiful minerals that are associated with copper, because copper produces these beautiful colors, mainly blues and greens. One of the prettiest that I've seen is this azurite. And I have that piece right here. That is actually not really enhanced. And unfortunately, the light here is kind of yellow. The lights aren't turned up all the way, so you really can't see the blue, blue, blue of this in this lighting. But if you took this out in the sunlight, that's just like the bluest blue you could possibly imagine. It's just amazing stuff. That's azurite, and it's azurite is a carbonate of copper. There's another carbonate of copper, which is chalcopyrite, malachite. Chalcopyrite's coming up. This is malachite, and this is a polished piece right here, which I stole from our store. So if you really like this piece, it's available after the show. We'll have to somehow get it back to the store, though. I promised them I would return it. But it produces these beautiful greenish color minerals, this malachite. There's one more that I really think is really beautiful, and it's chalcopyrite or bornite, which is a copper iron sulfide. And that's this beautiful color that turns, it has just a surface color, really. This turns all kinds of shades of blue and violet, and kind of reminds you of peacock. It's often called peacock ore. But if you freshly break it, it actually kind of has a golden color to it, kind of like a pyrite, actually. So this also is, I stole this from the store just in case anybody's interested. It's a lot cheaper. Also, copper occurs natively. You can actually go out and find the metal laying around. Oops, there we go. This is a piece of native copper. If you feel this is a pretty solid piece. If you come up and lift it, you'll see it's pretty heavy. Here's another piece that's native copper. Actually, that's both of these up here. So copper is one of the few metals that actually occur in nature directly as a usable metal. And because of that, it was really used from 8000 BC and hammered into various forms. It was the first metal to be cast into a shape using a mold around 4000 BC, and the first metal to be actually alloyed and mixed with other metals to create bronze, in this case, in 3500 BC. So the largest mass, I have to read this because I have to make sure I get it right. The largest mass of elemental copper discovered weighed 420 tons and was found in 1857 in Michigan. So that's a big nugget, 420 tons. Couldn't find a picture of it. It's found in all over the world, really. Here's just sort of where it's mined, but it's found all over the world. You can see the largest mine there in green is in Chile. Actually, here's kind of where copper is produced from. So Chile produces 30% of the copper in the world. Very important source. And if we look at where, it also has some remarkable things about it. In a place called Chuquicamate, there is a mine. Let's go there and look at it. That is actually the largest open pit mine in the world, sort of in northern Chile. If we zoom in a little bit more, unfortunately the projectors aren't showing it very well, but there's some little squares down here that are barely visible, and those are these giant trucks with tires the size of houses. So this is a big mine. Here's another one that's nearby. And I just wanted to bring this one up because this one you can see some of the beautiful green color that's coming from the copper, some of the salts of the copper as it leaches out of the mine tailings. So if we look at the production over time here, you can see that Chile became a major producer in the 2000s and now produces, as I said, about 30% of the copper. And our copper usage in general has gone up quite exponentially, which means that we're going to be in trouble soon. One of these days we're going to reach peak copper, because you cannot grow exponentially in a finite environment. That's the rule. So eventually we're going to run out there if we don't treat it well. But 80%, actually is a stunning amount. 80% of all copper is recycled. That's a really good amount. Most copper is used in electrical work. We'll get to that. And then a few other corrosion resistance, aesthetics, I like that one. But structural and heat transfer. Copper's a really good conductor of not just electricity, but heat. So we can talk about that in a little bit. So if we look at how much copper there is in the universe, it's not a lot. It's the 27th most abundant element in the universe, making up only 6 millionths of a percent of the universe. If we look at in the sun, you'd expect it to be the same, more or less the same, because the sun was made out of the stuff the universe is made out of. And so it's actually the 24th most abundant element in the sun. But if you look in meteorites, it's actually the 21st most abundant element, because a lot of meteorites are solid metal, and there's iron, nickel meteorites, and that does contain some copper as well. In the crust of the Earth, it's again the 24th most abundant element. Again, not the most, it's fairly rare. It makes up only 50 parts per million of the Earth's crust, but that's, again, taken as the entire Earth's crust altogether. It's concentrated in areas, obviously. 26th most abundant element in the oceans, very, very rare in the oceans. And it's the 20th out of 41 elements in the human body. So we do need it. It's in there. Copper is produced in supernova explosions and in white dwarf explosions. So it has to be made in exploding stars. So all the copper on Earth comes from exploding stars. It's second or third generation elements. Everything past iron has to be made in exploding stars or merging neutron stars. That's actually new data. The green stuff down here, that's all kind of new data. They just observed using LIGO these neutron stars merging, and they figured out that's where most of the heavy elements are actually made. So I mentioned that there are varying numbers of neutrons in the nucleus. So there's 29 protons, but there can be lots of different combinations of neutrons. Now these are called isotopes. Iso for the same tope's location, same location in the periodic table. But if you add up the number of protons, 29, plus the number of neutrons, then that's what this number is all about. So you can see you get everywhere from 52 to 80, so 29 different isotopes of copper. There's a lot of isotopes. However, these are all, if you treat these things chemically, you wouldn't be able to tell the difference between them. They all act the same because their electron structure, which is where all chemistry resides in the electrons, is the same. Only two of those, however, are not radioactive, and that would be copper 63 and copper 65. So there's two forms of stable copper in the universe, and they are created in different amounts. So copper 63 is about 70% of all the copper in the universe, and, well, at least on the Earth, and copper 65 is the other 30%. Now the other ones, the radioactive ones, some of them are more radioactive than the others, so we can actually take a look at that. These are the longest half-lives. What is a half-life? If I had a lump of copper 67, for instance, half of that lump would decay in 61.83 hours. So, and in another 61.83 hours, half of what was left, or a quarter, would be left after two half-lives, and so on and so on. So you can see all these half-lives are fairly short. Unlike uranium, uranium-238 has a half-life of 4.5 billion years. So the Earth is about 4.5 billion years old. So about half the uranium-238 that we started out with is still with us today. Now, one of those isotopes, copper 62, is actually used in PET scan machines. This is a specific kind of PET scan called a PTSM from the chemical that they inject into. The copper is a radioactive tracer, and it emits positrons. That's what the P in the PET scan stands for, positron emission tomography. And using this, they can actually image tumor blood flow and how tumor blood flow goes into the tumor and out of the tumor. So it's copper is an important element in PET scans. So if we look at the metal itself, we've actually seen some of the metal already. Copper is this beautiful reddish golden color. It's actually only one of a few of the metal elements that have a color other than gray or silver. And if you take a copper pipe and you polish it, which I did, this is sort of nice, clean copper. This is sort of what it looks like. I can pass these around. We'll pass one each way. Nice, clean copper has a nice feel to it, has a nice heft to it. This was from an ingot of copper that was sliced in half, and this was made with very little oxygen, and it was cooled very slowly, so the crystals had a chance to grow in this copper. So this is kind of very special. I used to have a slice just like that. I can't find it anymore. Oh well. If you want to see the giant piece of copper here at the Exploratorium, your best bet is at this exhibit here, which is called Floating in Copper. And that's over in the South Gallery on the other side where all the electricity exhibits are. So this is our largest piece of copper on the floor. I just thought I'd mention that. Some of the qualities of copper: it's pretty dense, about 9 grams per cubic centimeter. That's pretty dense. Remember what water was? What's water? 1. Right. And here's a few more here. And I have a whole bunch of blocks up here, more or less the same size. I'm one of these days. And come up after and feel the blocks, and even though they're the same size, they weigh different amounts. You see the biggest, 9 grams per cubic centimeter, the densest element is osmium, which we won't get to for years and years and years, but that's 22 grams per cubic centimeter. But here, we go up to tungsten, which is 19 grams per cubic centimeter, so that's actually super dense. If you lift that, be very careful. That little brick at the end weighs a lot. Don't drop it on your foot. It will leave a mark. Here's kind of a chart of the densities from the most to the least dense. And so tungsten's way up there. And then we go to lead and copper and iron and aluminum and magnesium. Oops, I skipped one somewhere. Titanium I skipped. And there's copper again. So copper is sort of mid between the light ones and the really, really heavy ones. It's a really soft metal. If we look at it on the Mohs scale of hardness, it's pretty soft. It's a number 3. So you can scratch copper with almost anything, with your teeth, actually. So it's pretty soft. One of its really cool qualities is that copper is a really good conductor of electricity. So here's a chart with the best conductors to the worst conductors. So you might imagine the worst conductors like gases and things like that down at this end here. But the best conductors are up here, and copper is the second best conductor of electricity. It's just barely under silver. But there's a reason we don't use silver wires in our houses, because it's a little more expensive than copper. Silver, and it's only a little bit better conductive, and also silver tarnishes. It's much more chemically active than copper is. So silver wouldn't work very well. So copper wire in our house is the rule. And I'm sure you've all seen copper wire. I didn't have to bring any here for you because it's pretty common stuff. But not only is copper a good conductor of electricity, but for the same reason, those loosely connected electrons on the outside, it's also a great conductor of heat. This chart looks just like the one we just saw, but this is in order of conductivity of heat, and copper is right where it was before, just under silver. Silver's a better conductor of heat. That means that sterling silver spoons are probably not very good for your hot tea, because the handle will get really hot. Neither would copper spoons be very good either. Might give you a aftertaste, copper. So if it's a good conductor of heat, that's useful as well. Not only can we conduct electricity with copper, but if we have something that's really hot and we want to suck the heat away from it, we can do that with copper. And this here is one of those things. If you have a computer at home, you'll notice that there might be something. This came from a server that I took apart. This is a heat sink. This sits on top of the CPU chip, which is in contact, thermal contact right here with the base. And the heat gets sucked up into this, and then fans blow through the fins and cool off the chip. It's a great conductor of heat. This is another heat sink. This one you might be more familiar with inside of your computers. This looks more familiar to people who do computer stuff. And it also has a nice slug of copper at the bottom that goes on top of the CPU, and then that heats up this piece of copper. And notice those copper tubes here. Those are actually not just solid copper, they're hollow copper, and they have some gauze inside of them, and this actually has a gas inside there that actually conducts heat. These are called heat pipes, and they conduct heat up to these fins here, which are then cooled off. So that's kind of more typical heat sink you might find in a computer, but it does still involve copper to get that heat away from the CPU. At home, I use copper to cook with because it's a good conductor. I have a set of Revereware, this is not a commercial, Revereware pots and pans at home, and these are stainless steel pots and pans, but they have a copper cladding along the bottom. Here's a piece of my cookware from home. And so you see this cladding is kind of placed on the bottom of the pan. It's kind of welded in place, and when the heat hits this copper, the copper spreads it out evenly along the bottom of the pan, which means that my egg cooks evenly in the middle of the pan, and I don't get hot spots. So you don't get a piece of really super done white and a charred yolk because there's a flame in the middle. This spreads the heat out because it conducts the heat evenly across the pan. And I believe we have an exhibit here, if it's out on the floor, called skillets. It was in the shop, but it may have gone out. I hope it went out. So copper, as I mentioned, is moderately rare, but it's not super rare, which means that copper only costs about $3.10 a pound. So not too expensive, definitely more than aluminum or iron. And that varies in price. That's one of those metals that's followed by the spot metal people. So you can get online and you can see how this price has changed over time. So just during this time here, you can see here from, the slide's not big enough for me to see here. So this is like September of last year, that it went down. But in November of last year, it went up. It spiked up for some reason. Who knows why? Maybe a mine closed down or something like that. But you can follow along the copper price, about $3.10 a pound. The copper atom is fairly large because it has those free electrons hanging on the outside compared to the hydrogen atom anyway. It has a pretty complex spectrum. This is the periodic table of spectra. And if you looked at magnified the copper spectrum, you can see it's got a lot of bright lines in it. It's pretty complicated. Iron was another one of those that had a complicated spectrum. So I think from now on, we're going to see some pretty complicated spectra. The sun, you could actually see copper in the sun's spectrum. If we look at, here's the sun spectrum. Now this one is kind of, I'm circling the copper lines in the solar spectrum, but this is kind of stacked. This would be a really long spectrum. It would be hundreds of feet long, but I stacked up the things here. This is from Kitt Peak Observatory. And so there's a few lines in the visible part of the spectrum that are from copper, right there and there. So copper exists in the solar atmosphere, as we talked about just a little bit before. It is in the sun. This is how we tell it's in the sun, is by looking at the spectrum of the sun. So what's it used for? Everybody knows uses for copper. I've already shown you one. Copper pipes. Pretty much everybody's got copper pipes in their house. They last forever, and they're pretty rugged. They're easy to piece together. They're easy to cut because it's soft and malleable. You can solder them together. It's just a nice substance to make pipes out of. It doesn't poison you like lead pipes, and like they're having a problem in Flint, Michigan now. Or the Romans. So it's just a good substance to make pipes out of. PVC tends to not last quite as long, a little too soft. But I have another piece here of practical use copper, but it's probably not as common as using copper pipes in your house. This piece here, which is a beautiful cast and forged piece of copper, is actually a piece of a linear accelerator. This is just a piece. They put a bunch of these together with brazing discs between, and they put them in an oven, and they all get joined together. This linear accelerator is used in a cancer radiotherapy machine. Here's what it looks like when it's all put together. And this goes into one of these radiotherapy machines, which I think are a modern miracle. Here you lay down on the table, and if you need radiotherapy, you need X-ray therapy for a tumor, this machine can actually shape the X-ray beam to the same shape of the tumor as that it's pointing at. In other words, they take a 3D model. They make a 3D model of your tumor using a CAT scan or a PET scan. And once they have a 3D model of the tumor, they actually shape the beam. So as it moves around you, the shape changes because you're looking at different aspects of the tumor. But you're only exposing the tumor to all those X-rays. You're exposing the rest of your body to far less radiation. And these are manufactured right down in Palo Alto by a company called Varian, who was down there before HP, actually. It's shocking. Actually, here's where it is. There's the accelerator right there in the head. Then the beam gets bent and then shaped. Here you see a tumor-shaped beam there. So it's also copper is also used in construction. Some places, if you have a lot of money, you can put a roof on your building that's made out of copper. And here, it doesn't look all shiny here, but because it's been out in the weather a lot and it's changed chemically to have a beautiful green patina on it. This is Minneapolis City Hall and has a nice copper-clad roof that they won't have to replace for probably 100, 200 years. We have buildings here in the city that are very coppery too. One of our sister museums in Golden Gate Park, for instance, the De Young, is completely clad in copper. And right here, this was far enough along in its aging to have aged into this black copper oxide. If you start off, here's the side of the building. When you start off, it's really shiny copper, like the pipes I passed around. And then it starts going this reddish copper oxide color. Eventually, it goes black. And you can see that the De Young is beginning to get this beautiful green patina as well. That the De Young, by the way, the copper skin on the De Young, they used over 1 million pounds of copper, 2,200 cubic feet of copper on that building. The nice thing about what's happening here, though, is once you get that coating, it kind of protects the copper underneath. And so that oxide is really a protectant. Aluminum does the same thing. It's called passivation when you get that oxide coating on the copper. Probably the most famous example of a green coated structure, of course, would be the Statue of Liberty, which is coated with copper and has that beautiful copper patina as well. That green copper stuff is called verdigris. That's the green copper carbonate. And you see it on basically all copper structures. So we mentioned that you can actually mix copper with other metals. If you mix copper with this, which is tin, you get bronze. You get this. This is a spare from an exhibit we have here called, oddly enough, Bronze Hand. I think we missed an opportunity here. I think they shouldn't have done it like this. They should have done it more like this. But that's just me. So bronze, we have a couple of really nice bronze exhibits in the museum. Out front, we have Archimedes, the dishes, the whispering dishes. And when we opened here at the museum, we worked with the Crucible over in Oakland, and they cast us a beautiful bronze bell, which is outside, right out here, just outside the door here. And of course, bronze has been used for statues for thousands of years now. Since the Bronze Age, I would guess. Don't quote me. Now, if you mix copper, not with tin, but with zinc, this is zinc, you don't get bronze, you get a different alloy, you get brass. And brass, of course, is very famous for being made into instruments, and I think I have another instrument here that was made out of brass, or maybe it's not here anymore. Where did it go? Oh, well, I had a brass bell up here. It's not here. Oh, I forgot to mention about the conductivity using in wires, but also there's flat wires. This is a circuit board, and on the back of the circuit board, I'm digressing here a bit. Forgot a prop. On the back of the circuit board, there are wires that are actually bonded onto this green fiberglass, and those wires are actually copper. They look silvery here because they've been plated with nickel to keep them from corroding. But this, by the way, this circuit board was from my first computer. I want you to know this is a 4K memory board, 4,096 bytes. If you populated your current computer with these boards, it would take 250,000 of these boards just for 1 gigabyte. And that would it would cost you probably about $200 million for the RAM in your computer if you did it this way. And you'd have to have a dam to run it. This was a S100 computer back in the good old days. CPM. Anyone ran CPM? All right, a few people. Probably in the late 70s. Yep. Okay. I still have my S100 machine at home. It still boots off 8-inch floppy. Okay. One more interesting thing that we're going to talk more about tonight is copper in blood. Now, we're used to not copper in our blood. We're used to iron. We have hemoglobin. And there's an iron atom in the middle of that molecule. But certain animals, as you can see here, have a couple of copper atoms in their oxygen-carrying molecule, which, by the way, is not bound inside of a cell. It just is free in their blood. And that creates not red blood, but blue blood. And one of those creatures is a crustacean, which is the horseshoe crab, which is actually, and here they are bleeding horseshoe crabs, and that is their blood there, that blue liquid going into what look like milk bottles, is horseshoe crab blood. Now, they don't kill the horseshoe crabs. They just take a little bit of blood, and then they throw them back. And this is not called hemoglobin. This is called hemocyanin. And this is used to carry oxygen through the blood. And because of the presence of copper, their blood is not red, it's blue. And this is actually used in medicine as a test for bacteria. If there are bacteria in a sample of whatever, if it's on equipment or if it's in an injectable, if you mix some of this, well, some of the product from this, not the actual blood, it is a clotting agent that will clot it up if there are bacteria. So almost everybody can thank the humble horseshoe crab for not having bacteria injected into them. That you wouldn't want that. Prior to 1977, when this process became useful, there was a much slower process and was more expensive because they had to use bunny rabbits. So bunny rabbits or horseshoe crabs, you'll have to make a choice here. Copper does appear, it's essential to all living organisms. It's just a trace in your dietary supplement. People who have a macular degeneration, there's some copper that you take in your vitamins there, and you take zinc as well. It's a key constituent in a respiratory enzyme in you, so you need it. In humans, it's found mainly in the liver, the muscle, and the bone. And your bodies contain about 1.4 and 2.1 milligrams per kilogram of body weight. So you do have just a few milligrams of copper in you, not even a gram. Okay, so when we think about copper a lot, we think about coins. The nickel. You don't normally think about copper when you think about the nickel. The copper is actually 75% copper, the modern nickel. It's only 25% nickel. So the nickel should be called a copper. The quarter has 100% copper in the center of it, the current quarter since 1965. Before that they were silver. But now our money actually doesn't have any actual value. And it's copper, it's a nickel copper plating. So if you look sideways at a quarter, you'll notice the copper in the middle. That's 100% copper in the middle. Now the penny. The penny is, of course, looks like copper, and the 2018 penny, we'll get to that. Originally, in 1793 to 1837, it was 100% copper, but then they started mixing other metals in for corrosion resistance and make it a little harder to wear down. So we had copper with 5% tin and zinc, which is kind of a kind of a bronze brass mixture. And then it went to an 88% copper to 12% nickel, cupro nickel. From most modern, well, not most modern, but up till 1962, they were 95% copper and just 5% tin and zinc. So that was pretty good. So if you go back and look at your pennies before 1962, they're mostly copper. Now, in 1943, there was an exception. They made pennies out of steel because during the war, the copper all went to the war effort. But that's just an exception. It's just 1943. But then after 1962, they went back to the same mixture again. And today, shockingly, after 1982, pennies are only 2.5% copper and mostly zinc. There's zinc on the inside. You can actually drain the zinc out of a penny if you drill a hole top and bottom, hold it in pliers and apply a torch, and the zinc will drain out of the penny. You can try that at home. Be careful. Last month, we did, last Everything Matters, we did nickel, and I nickel-plated copper pennies. So the pennies came out silver. Excuse me. To be fair, this month, I figure it's only fair to take nickels and copper plate them with, copper plate them to make them coppery. And it's easy. You can do this at home. You just take a bath. Into that bath, you dissolve copper sulfate. You put in a copper electrode, bring out a battery, you attach the positive to the copper and the negative to the nickel. And then copper ions flow from the copper electrode to the nickel, and slowly but surely the nickel gets copper plated. So I have nickel plated pennies and copper plated nickels, and there's some of them are up here. You can sort of see it's coppery. Here's one that's only half. I don't know if I can show this to the camera or not. This one's only half plated. Actually, here, I'll show you a slide. So there's a half plated nickel, and I'm not happy with the way these came out, by the way. The nickel-plated pennies came out really shiny, but the copper-plated nickel, I'm getting very confused talking about this. The copper-plated nickel came out kind of matte. I think the crystals are growing out of the nickels themselves. My fanciest example of copper plating that someone showed me just the other day, I'm so happy they did, is the copper chopper by artist Paul Yaffe. And this is a beautiful piece of artwork where he copper plated everything he could copper plate on the chopper. So I want to leave you now with a elemental haiku from Mary Soon Lee. Before the Bronze Age, before history began, bent to the smith's need. Next month, we move on to the next element. Element number 30, zinc. Woohoo! Zinc, yes. And that will be next month, June 21st at 8 o'clock. I also do a talk called Everything Matters. Called Full Spectrum Science. And since the next one here is in June, this month is going to be sound. I'm doing sound this month. It's on the 4th Thursday and the 4th Sunday of the month, and I have the wrong slide. But I can give you a preview of what's coming up in June. What's coming up in June, we're going to talk about how fireworks work. So that's going to be fun. Come out and find out how those beautiful fireworks work. That's in June. So we have sound this month, fireworks next month. And thank you very much. Don't go anywhere because we're going to get Ashley's talk up here, and she's going to talk about spiders. So if anybody's creeped out, any arachnophobes in the audience, close your eyes. Thank you.